When we save a file to a USB drive, we assume the data just sits there, perfectly still, waiting for us to return to it. As the VO says speed of light, the glowing energy pulses intensely. But digital information is actually made of electricity, a medium that natively flows, bounces, and disappears at the speed of light. We process those electrical currents using physical logic gates inside chips like these. But these gates are volatile. The moment an electrical input stops, the gate forgets what it was doing. To solve this, engineers developed the D-type flip-flop. The D stands for data. It is a circuit specifically arranged to act as an electronic trap, designed to grab moving electricity and hold it in a stable state. The anatomy of the trap is simple: one input line for the data and two output nodes, labeled Q and Q'. This memory circuit is engineered to ignore the data input for the vast majority of its operation. To record a piece of information, the circuit must first be taught how to go completely deaf to the noise of the outside world. When power is first applied to this hardware, it triggers a hard reset. The memory slate is wiped clean, defaulting the stored value to 0. These two output nodes operate in strict opposition. If Q is a 1, the underlying physics force Q' to be a 0. They are always perfectly inverted. In this deaf mode, you can flick the data input as wildly as you want, and the outputs will refuse to change. The system's truth table maps this behavior. Multiple scenarios result in a no-change state, where the circuit ignores the varying data inputs on the left to maintain its current output. Breaking this stalemate requires an external trigger, the clock. The circuit ignores the steady flow of power, reacting exclusively to the clock edge, the exact millisecond the signal transitions from 0 to 1. This stubborn refusal to change is the mathematical definition of artificial memory. To create a single bit of memory, we load a 1 into the data input, while the system clock is low. At this stage, the circuit is still deaf. The instant that separate clock line spikes, hitting its rising edge, the trap opens. The data transfers into the Q output. As the clock drops to 0, the Q output locks. Even if the data line flickers between values, the output holds its state. This timing chart traces the result. While the input lines fluctuate, the Q output maintains a flat line, holding that 1 over time. In digital electronics, memory is a specific electrical state held static by the precise timing of a clock pulse. This physical D-type flip-flop holds exactly 1 bit of data. Modern solid-state drives and processors take this exact gate and clock mechanism and replicate it billions of times across a microscopic silicon grid. While early technicians wired these gates by hand, modern engineers designed these massive arrays using hardware description languages like Verilog. That physical reaction to a rising clock edge is now written as a single line of code, posed edge click. This command acts as the gatekeeper, dictating the exact microsecond billions of memory cells trap their incoming data. From the smartphone in your pocket to the servers routing global internet traffic, active memory relies on these humble logic circuits, waiting patiently for the clock to tick.